Okay, in this experiment, we're going to be looking at stretching springs and rubber bands. You probably would have seen a theory lesson before this, but in essence, what you're doing, let's go with this spring idea first. What you're doing is you have a spring and you have a mass at the bottom, and that mass exerts a force. In this case, it's the weight of the mass. Now, just be careful there of mass and weight. Remember, the weight of an object is the mass, which is in kilograms, multiplied by g on Earth, which is 9.81. So if this were 100 grams, then the weight would be 100 grams, but now I need to convert that into kilograms, multiplied by 9.81 mg, giving me 0.981 newtons. So we do need to be careful about that. Okay, I'm looking to investigate whether Hooke's law holds true. Remember from the theory, the force is equal to a constant times by the extension. So if I increase the force, the weight on this spring, I will increase the extension, not the length, the extension. So what am I going to do? Well, I'm going to control the amount of force I put onto this spring, and I'm going to measure the extension by which it stretches. So my independent variable that I'll be using, the one I am changing, will be the weight, which in turn is the mass. And my dependent variable, the one that I'm measuring, will be the extension. We'll do that probably in centimeters. However, we have a small problem in that the spring itself has a certain length. And I'm not interested in the length, I'm interested in how far it extends. So what I'm going to do is, my table is going to have, first of all, the mass, because I'm interested in my independent variable first. And then, in actual fact, let me draw it here because I'm going to need a few columns, right? So I need my mass first in grams. Then I'm going to measure my length that I have on the spring, the overall length, once, twice, three times, and average it. And that in the first instance is going to be my table of results. But then what I'm going to do is, we must start with zero mass, and we must start with a certain, and so work out what the length is with zero mass. Then I'm going to work out, first of all here, the force, which the mass exerts in newtons. Remember how we did that. And then finally, I'm going to work out the extension by taking away this value from each of the subsequent values. Centimeters. So there is the table of results. I'll show you the setup, and then I'll show you a set of results that I've taken. Right, now, here is my spring, and I've got an elastic band at the back because it's that we treat both the same way. But let's look at the spring first. I have my spring of a known length, and as I place on this weight, it starts to stretch. And as I continue to add weights, it starts to stretch even further. Now, the difficulty of this is being able to read off exactly what point you're going to read from the spring onto the ruler each time, and also making sure that it's close enough so you're able to read off what's going on. A set square might be quite useful here. Placing a set square on the ruler, finding the point you're after, and then reading directly off. Let me turn that to the side to show how that's probably better achieved. Because otherwise, if your eyes are viewing this way, you get this parallax problem. So what you could do is achieve a fixed point on the spring and then work out where that relates on the ruler. Alternatively, you could try and move the ruler even closer so you don't get so much of an error. And now it might be easier to read because you're just directly across. But either way, we first of all, in our first instance, want to measure the absolute length. So this would be 52.3. And then subsequently, this is for 200. If this were 59.1, we need to minus 52.3 from it in order to just look for the extension, not the overall length, just the extension. Similarly, if I put 3 on, I'm not looking to subtract this one from the previous one. I'm looking to subtract it from the very first one in order to give me the extension in question. If I were to do a rubber band with exactly the same setup, it's a little trickier to measure that first overall length. So I suggest you hold it until it just becomes taut, measure, and then start applying your weights. What's interesting here is as you apply, you'll notice that it's different on the way down to when you start releasing weights on the way up. So for a rubber band, I want you to apply weight and then remove weight so we can see whether there's any difference. But for the spring, just applying weight, just applying weight is good enough. Okay, so here are the results from the stretching of the spring. We applied a mass in kilograms, so 0.1 refers to 100 grams. All the way down, we took it down to 0.9, 9 lots. And then the force is going to be, the way that we move from one to the other is multiplying that by 9.81, because m in kilograms times g gives us the force. Explained that just a little bit earlier. And then we looked at the length, the absolute length of what you measured from the meter ruler, 3 times plus an average. And you can see that this is getting longer and longer as more and more force or weight is applied. But these are the absolute values, but what we're looking for is the extension. So how we achieve this is, this extension is the difference between there and there. However, where some people fall foul is that they think the next extension is going to be the difference there. It's not. It's going to be this difference because you're looking at it from originally. Then this number 12 is going to be the extension from the original value. And that continues all the way down. So you have an ever-growing extension. So with increasing force, you have an increasing extension. And let me just show you all the results so you can jot them all down if you need a set of results for yourself. Good, okay then. So what we're effectively trying to work out is we're going to try to see if the force is equal to is proportional to the extension, i.e. with a constant k. And when you draw a graph, of course, all graphs should have the independent variable down here and the dependent variable along there. The independent in this case was the force in newtons, and the dependent was the extension in centimeters. And what we should get is something looking like a straight line. However, there will be a case in which you may have the spring stretching and return to its original length. But if you give it too much force and stretch it too far, it goes beyond its elastic limit. So eventually, the spring will do something like that. In other words, at that point, it has overstretched and it will no longer go back to its original position. So this is the elastic limit. And you might find that if you load the spring enough. If you keep loading it, it will have permanent deformation. Okay, when you do the, so that's for a spring. When you load the rubber band, you are going to see a difference in the loading and the unloading. And the results for those are in the link below the video. But what you have here is, you have, and I just need to remember which way around we do this, it looks something like that, for the force again in newtons and the extension in centimeters. And when unloaded, it's going to give a slight difference. I'm just wondering if that's the right way around, the force extension. Yes, I believe that's the right way around. So what you'll notice is between loading and unloading, it won't behave identically like a spring where it goes back up and down along here. And you won't really need to worry too much about the theory of that. Needless to say, though, that that area in there is some energy given out, hence heat. So rubber bands heat up, rubber things heat up. Okay, good. Hope that makes sense.